Of course, I'm a huge fan of science, but I'm also quite a fan of philosophy. This idea of how we know what we know. And of course, that's the tagline that we've been using for Astronomy Cast since the beginning of the show. What methodologies do we use to examine the world and think about some of the scientific problems that we face? The more esoteric, the more abstract our knowledge, the more rigorous that we have to be in the way we examine the evidence, the way we think about our assumptions, our biases. It's complicated work, and it's the work that philosophers do very well. So my guest today is Dr. Sam Barron. He is a professor of philosophy at Australia Catholic University and has been doing a lot of interesting work in examining the philosophy of science, specifically in the worlds of relativity and time travel. How do we bring together quantum mechanics and general relativity? A lot of this stuff is very cutting edge and is very complicated and requires a certain amount of philosophical horsepower brought to bear to assist as we develop these theories that are beyond our ability to observe directly with our own eyeballs. So it's a wide-ranging, fascinating conversation. I hope you get a lot out of it. I know I did. Here's the interview with Dr. Sam Barron. So what does it mean to be a philosopher of science? I mean, aren't all PhDs philosophers of science?
Yeah, I mean, like the PH in PhD does stand for philosophical. Yeah, what does it mean to be a philosopher of science? So I suppose the way I think about it is that there are certain questions that scientists are either not in the business of answering or don't have the scope to answer because they have to work inside a certain paradigm. And so there are some questions that I think philosophers can then come in and help to answer, in some cases to help develop science, but in other cases to sort of flesh out the picture of the world that science might give us. So here's a sort of example of questions that are asked in the philosophy of science. So scientists are really good at coming up with explanations of things. So, the gravitational, a sort of black hole will explain the gravitational lensing of light from a distant star. And so we can sort of come up with an explanation of a particular astronomical phenomena that we see. But science is not necessarily going to tell you what explanation is or how it works. And so philosophy can come in and tell you what explanation is, how it works, what it is for one thing to explain another, and give you different theoretical ways of working through that, which can then feed back into scientific method. And in fact, if you look at the history of science, you'll see a sort of very, complex interplay between people thinking about the methodology of science and thinking about science from a sort of philosophical perspective and people doing science, and those two things sort of working together for the most part. So I think philosophy of science is thinking about science rather than doing science.
Right. And I mean, I am so excited by the scientific method when it was developed. I mean, obviously, I think we human beings perform the scientific method all the time when we're trying to figure out what's making that knocking sound coming out of our refrigerator, or where did we put our wallet, right? That you're doing science. You're like, did I check, is it in the drawer? No. Did I put it on the bed? No. Is it in my pants? Yes. That was science. And so a certain amount of science is just done because it's our instinct. It's the way we look at the world. But there was a moment when people started to follow a rigorous method where the scientific method ran counter to their instincts. What do you think was that moment that we sort of made that transition over?
Yeah, I mean, I guess because I'm not a historian of science, I'm not sure I know historically what the time was, but I guess...
Well, more philosophically,
yeah.
Like what are we doing when we are running experiments, disproving hypotheses, and we're way beyond what we can wrap our heads around easily?
Yeah, I mean, I think what's happening is that we're refining the scientific method. So in the example you gave, where you're just sort of looking for your keys and you rule out various options, there are better and worse ways to do that, right? And we use ways that we've developed as heuristics for getting around the world. And yes, some of them can be scientific, but some of them are quite bad, actually. And some of them lead us astray in a lot of different ways. And so I think the point at which science starts to push back against our intuitions is the point at which we start to do science better. And once we start to refine the scientific method, and refinement of the scientific method is relatively recent in my view, right? We've been doing science for a long time, but we've been doing science better for a much shorter time. And I think that indeed that philosophy has a bit of a part to play here, because the refinement of the scientific method is happening by philosophers and scientists working together, thinking hard about science and trying to work out how that goes. And so I guess that's how I would put it philosophically.
And so what is that moment, do you think? When you say we've been doing science better, what are the hallmarks of better done science?
I think controlling for weird correlations, I think is an important one, right? Like, that lots of people, confuse correlation with causation. The old adage, don't confuse correlation with causation. But it turns out to be very difficult to actually, when you've got a sea of correlations, a sea of statistical information, to actually pull out causal information from that sea. And so we have developed tools and methods for controlling for various variables in order to identify, the causal handles of the world that we can pull in order to make things happen. And we've been getting better and better and better at that. And, I think a lot of elements of science are in the business of refining that aspect. And that sort of historically, you see people working out new methods to control for things that they couldn't previously control for, so that we could get a better handle on the causal structure of the world.
I mean, is part of it just being aware of your potential biases? Like, now that we've named the biases, the confirmation bias and all the various ways that we can, at this point, I think there's like a list. There are dozens of biases that we can go into. Just by naming them, I think we can kind of go through that list and say, am I hoping for a certain outcome? Am I right? And I wonder if just that sounds like philosophy, right? Like, that's the philosophical challenge, to identify and give these things names and definitions.
Yeah, I think that there's definitely philosophical work there to understand those biases. I also think there's a hell of a lot of psychological work there to be done to understand why it is that we think the way that we do. And like at a deeper level, I think one of the challenges with science is trying to work out which things that we observe are because of us and how we function, versus which things are because of the way that the world is. And we're constantly trying to work out how to extract the kind of idiosyncratic human perspective from science to get a better picture of the world, right? So for instance, we used to think that the universe revolved around us. And, there are descriptions of the universe where, you can kind of paint it that way. Even in relativity, you can kind of paint it that way. But we now recognize that there's nothing special about us. There's nothing special about our perspective. And in fact, the universe doesn't revolve around us. And we've got a much better picture because we've extracted some of that human perspective from science. And so I think, yes, there's those biases. Yes, there's that sort of psychological makeup that we have to deal with. But there's also just our perceptual faculties and the nature of observation, and trying to work out which bits of the universe that we see are due to the lens that we look at the universe through versus which bits are due to the universe itself is very, very difficult. And I think we're still trying to work out exactly how to, get as much of the human perspective out of science as we can. And indeed, if we can actually do that, it may be that there are some things that are sort of deeply perspectival in nature in science.
And then there is a weird, I've been reporting quite a bit on this. There's like a weird time, and I'm sure you've perceived it as well, just this distrust of expert opinion. Is that science's fault, or is that like culture's fault? Where do you think this distrust of the methodology is coming in? Because it feels like there's no technique that has had more time and thought put into getting the methodology right, and yet that doesn't seem to be transmitted.
Yeah, I think it's hugely complicated. I think it's probably a mixture of all these things. I mean, scientists are better and worse at science communication and explaining what they do to other people. And there are some times where I watch people explaining, for instance, like how climate models work, or why it is that the evidence from a climate model counts as evidence. And you see a scientist explaining this, and they don't do a great job. Sometimes they do a great job, sometimes they don't do a great job, and it just leaves an opening for people to jump on them and attack and, come up with this counter narrative where the evidence is not really evidence. And so I think there is probably something there to do with the the public relations side of science and the marketing side of science. And there is also a cultural element. People have all kinds of, culturally enforced beliefs that can be very stable and very difficult to move. And some of those will just wash out any kind of evidence that you might have, and like are kind of almost tailored to do that so that you can preserve certain kinds of perspectives on the world. So I think that there's like both of those elements in there. I also think that there are just some genuinely difficult philosophical questions about how science works that mean that it's sort of difficult to know what to think about those questions, and it leaves an opening for people. So, for instance, there's an old philosophical problem with science concerning induction. How do you know that the sun will rise tomorrow? Well, you've got all this evidence because it rose every day in the past. But of course, that doesn't guarantee that it's going to rise tomorrow. And so all you can do is like take a bet on whether it's going to rise tomorrow. And so this is what, and you've got people want to try and shore up induction and make it that you can't be sort of skeptical about induction. There's lots of philosophical work trying to do that, but no one's ever really solved the problem. And so when you get to something, for instance, like climate change, what you're dealing with often is like abductive evidence of the kind that abductive or inductive, like you're either dealing with inference, the best explanation, or induction over time, where you're going from past data to future data. And both of those things have a sort of like logical gap. They don't ensure or guarantee the conclusion that you're trying to draw. And because there's that gap, of course, people can insert their skepticism right in there. And there's not a lot you can do except sort of like churn through the philosophy over that issue and come to a view about how it works. And I think it's just genuinely difficult sometimes.
Yeah. Yeah. I mean, it is interesting. I mean, your example is perfect because, the sun will rise tomorrow, but one day it won't. And that day will be when the earth has been charred into a cinder and engulfed by the sun. And then that'll be the last day on earth because the earth will be destroyed. And that's a finite, you could count that number of days until you reach that number, but it's probably not tomorrow.
Right.
And yet you can't guarantee 100%. And aliens could destroy the sun tomorrow, and so on. And so, so now you are specializing specifically in where philosophy and physics, astrophysics, cross one another. So can you explain your work a bit?
Yeah, sure. So one of the areas that I look at is the nature of space and time in particular from a philosophical perspective. So I work on the philosophy of time. So one of the things I look at is time travel. But the sort of research that I've been doing most recently involves looking at sort of recent developments in physics and trying to understand what those developments in physics might be telling us about the world. So there's a sort of interesting crisis in physics at the moment. We've got two big theories, general relativity and quantum mechanics. These are the best theories we've ever developed. They're extraordinarily well confirmed empirically. They're, mathematically complex. They're very, crowning achievements of physics over the last century, but they conflict with each other. So quantum mechanics and general relativity, in some sense, they both can't be right, or there's got to be some third theory that manages to unify the results of both and sort of iron out the wrinkles between them. And so this is the area of quantum gravity that people are trying to develop. And what you're trying to do there is take the sort of quantum story that you give for particles like, quarks and leptons, and you're trying to extend the quantum story to gravity, and you're trying to give a quantum account of the gravitational field. It's very difficult. People thought it was going to be so like after general relativity and quantum mechanics were developed. I think there are some physicists on the record for saying, "Oh, physics will be finished in 30 years," and that was in the 1950s. Yeah. And I think things have just gotten worse since then.
Yeah, Einstein took this problem to his grave.
Right. Yeah, and string theory is an example of one of the theories that's come out of this area, but there's a bunch of other theories. And what's interesting about some of these theories is that they seem to suggest that space and time are not sort of basic features of the world, that space and time might be something that arises at certain levels, but that at a deeper level is not there. So to just sort of take an analogy, you could think of certain thermodynamic properties like heat and things like that as being emergent properties. At a fundamental level, what you have are particles whizzing around, And there's not heat there per se, it's just like mechanical interactions between particles, but then you get heat at this high level. And some people think space and time might be like that, right? So space and time exist at a certain level, and then at some deeper level there's something else. Question is, what is more fundamental than space and time, and what's the relationship between that more fundamental thing and the sort of world of space and time as we know it? And this is where sort of philosophy and physics, I think, are coming into contact, because we are hitting a realm of physics where we can't empirically test the views that we're coming up with. So there's no data that we have that we can use to test the theories against. There's not even experiments that we can like plausibly develop at the moment that we could test some of these theories. And so a lot of what we're doing is trying to like mathematically and conceptually wrangle a whole bunch of stuff together to come up with a new theory. And in that is a lot of philosophical work to try and understand how concepts like space and time might connect to something at a deeper level and what that deeper thing might do. So what I'm trying to do as a philosopher is look at these theories and try to come up with some models of how the world might be whereby space and time are not basic, using tools from philosophy from the last, couple of thousand years.
Yeah, I mean, I think all the way back to like Plato asking this question, are we seeing reality? Or are we seeing some filter? And he imagined some, Plato's cave, and he imagined some perfect versions of various shapes, but we can only see these shadows of their actual form. And I mean, what we see as reality, we know is not reality, because we're seeing it filtered through our brains and our eyes and our ears. And I don't even know if what you see of the world is the same thing that I see of the world. And we can both identify a tree and say that it's green, and we think we're seeing the same color, but we don't even know if that's true. So, I mean, this idea, are we seeing base reality? This is, as you said, it's thousands of years old concept to think about. Have we made any progress on that question?
I mean, yes and no. I think it's a sort of classic philosophical answer I'll give you. We have, insofar as there are certain things that we have discovered quite strikingly, I think, that are due to our perception rather than part of the world. And so we have sort of sorted out some of those, sort of found some of the shadows in Plato's cave, if you like, and primarily using science. So here's an interesting example. Very plausible to think that colors are out there in the world, right? That when you see a red chair, that the redness is sort of in the chair itself. And that if you were to strip all of humans out of the world and all consciousness and all perception, that there would still be colored objects. Good reason to think that that's just not true. That color is in fact an interaction effect between us and objects. It's light bouncing off things that produces colors. And if we weren't there in the world to perceive colors, it's not clear that color would be there, right? So there's an example where it's sort of like something we thought was part of the world is not in fact part of the world. And I think we've sort of got a pretty good sense of that. Space and time, in the shift between the sort of late 19th century into the 20th century, something like this happens. Up until Einstein, we think that all of us occupy the same moment in time, and that there's this sort of sheet of time that cuts across the entire universe. Like everything in space is located at the same moment of time, and then the next moment happens, and the next moment happens. We're all sort of like carried through. But in relativity, that's just not true, right? Depending on how fast you're going, the temporal distances between things contract and expand. And so our perception of the world as this sort of like stable thing in time marching forward turns out to be a function of the fact that we happen to be relatively low energy, slow moving objects. So there's a sort of another example. And so the question really for science is like, how much of it is in us and how much of it is in the world? And the question about space and time could be a little bit like that. It could be that some of the aspects of space and time themselves at an even deeper level than relativity has shown us are part of our perception rather than part of the world. Or it could be that, those aspects are really part of the world. And that's sort of I think something that we're grappling with a little bit in physics at the moment.
And I think when you think about things like observing particles, the double slit experiment, like there's something really weird going on there that we're getting one result in one part of the experiment and a different result in a different part of the experiment. And the only difference is that we're making an observation. that that feels like one of the first times, I'm sure when physicists got to that was terrifying, because now you're disconnected from reality in a way that's a little bit more, I don't know, existential to me, maybe.
Yeah, I don't know what to make of quantum mechanics. It freaks me out. Entanglement and like measurement and how this works and what all this means, I just don't know what to make of it. And you look at the interpretations of quantum mechanics. So you've got quantum mechanics, which is a chunk of mathematics, and it's extremely accurate predictively, right? Like the statistics that you get from quantum mechanics reflect the way that the sort of statistical information that we gather from the world when we start measuring particles and interacting with them. But we have no idea what it means, right? We have no idea what this mathematical thing that is extremely well confirmed is actually telling us about the world. And there are all these different interpretations out there. There's the sort of interpretation that's in the direction of the one that you're talking about, where maybe there's something like quantum mechanics is reflecting some feature of our knowledge and the way that we interact with the world. But there are much more radical versions, right? Like the many worlds interpretation of quantum mechanics says that every time you perform a quantum experiment, it's not the case that there's just sort of, we gain a new piece of information, but the world itself is splitting in some sense. And like both of the outcomes are there. It's just that you happen to exist in one of the outcomes. And it's just like, well, this is completely, this is, I think, metaphysics at this point. I think we're deep into philosophy once we're starting to try and provide these interpretations of quantum mechanics. And so, yeah, I think quantum mechanics is a good case for this sort of thing, and I have no idea what to think of it.
There's just like a bunch of philosophers working in quantum mechanics, and they're just shell-shocked at this point?
I mean, there are a bunch of philosophers. There's a bunch of people who have PhDs in both philosophy and physics, who are working on interpreting quantum mechanics. And I think there are definitely some of them who are shell-shocked. There are some of them who think they've got it worked out, who think they know what the sort of truth of the matter is. Yeah. There's quite a big proportion of them who are fans of the many worlds interpretation. But yeah, I think there's a lot of just scratching of the head going on here.
Yeah, well, I think Sean Carroll is sort of the classic example of someone he's diving in with both hands, both feet. Anyway, he's jumping into, like, he's, more of a physicist originally, and now really going deep in on the philosophy side, trying to understand this, which is interesting to me, because I think, like, as it is an additional headache on top of, like, as a physicist, you can just perform your experiment, see the result, and go, I don't care how it works. Like, it just gives me the result. It seems to satisfy this math. I can make a prediction with my mathematics, and I don't really need to know that deeper meaning. So let's talk about that deeper meaning. How do you search for a deeper form of reality?
Yeah, I mean, I think it is notable that the sort of person you're pointing to, Sean Carroll, but also the people in physics in general who are interested in philosophy are more on the theoretical side rather than the experimental side. I think that experimental physicists, by and large, are just, like, do the thing, get the results, build your particle accelerator, shoot it at a wall, and you're done. The question is how it is when this is a very interesting question. How is it that when you've got sort of theory that's maybe very well empirically confirmed, like quantum mechanics, but we don't understand it, how it is that you go about working out what the truth of the matter is? And there's disagreement about this, but one option is to look at what is sometimes called the theoretical virtues. So in addition to being empirically well confirmed, a theory might have other qualities that we like. So it might be very explanatorily powerful. It might give us a deep understanding of things, or it might be very elegant. It might be very simple. Like Occam's razor might be being used all over the place to cut away all the things that we don't need. It might be very fruitful. It might, lead to things in the future. There are lots of other properties of scientific theories beyond their empirical adequacy or empirical confirmation that we care about. And one way of working out how to sort of find this deeper meaning or this deeper reality, as you're calling it, is to look at those virtues and basically pick the theory that scores the highest on the things that we care about. One of the sort of like difficulties there, though, is that there's a philosophical question about what are those virtues and do they actually track truth? when we look at the elegance of a theory and you look at science, you look at mathematics, indeed, a lot of the choices that people make about theories are made based on sort of things that look a little bit like aesthetic considerations, like elegance and symmetry and all that kind of stuff. Physics is like up to its eyeballs in symmetries. Why? And, you could ask the question, well, how much of that is a reflection of us and the things that we like? Maybe we just happen to like those things, and so we look for them in our theories. And how much of it is like some sort of part of the way the world works, that it sort of seeks to produce simple systems or seeks to produce elegant systems or something like that? And I think that's just a really hard question. But that's like a level above the question of how it is that you work out, say, which interpretation of quantum mechanics to accept. You've got to then rise again and go, well, how do we work out we work out which interpretation of quantum mechanics to accept?
Well, that just sounds like a philosopher's job right there. Like that alone is several people working on how do we work out how we work out. That sounds, but I just sort of think about that. Like, nobody ordered quantum mechanics. Like, if you're looking for that checklist of like, these things they're easy to understand and they're elegant and they are, like, at no point does quantum mechanics fulfill on any of those promises, and yet it seems to be true. And so there are times actually when you have to be dragged kicking and screaming into a deeper understanding of reality. Now, let's specifically focus on your work with relativity, black holes, time, things like that. So where are they hanging together in your mind?
Yeah, so I mean, I'm interested in black holes for a couple of reasons. One reason is because they're very odd objects potentially when it comes to time, because they have the capacity, it seems, to roll time up and turn it into a loop in such a way that you could, in principle, if you can get on the loop, jump out at some time in the past, which means that a black hole, on some descriptions, it's a little bit tricky here because you kind of got to grab a theory of physics off the shelf of the geometry of black holes, and you've got to make some assumptions about how black holes work, and you put it all together. But on some pictures, you get something that looks like a time machine arising in nature out of a black hole, and that's super interesting. Philosophers have been interested in time travel, as long as we've had the notion that there might be such a thing, and in particular because a lot of people, and physicists in particular on record for saying this, a lot of people think that time travel leads to paradoxes that make it impossible. So, the classic grandfather paradox: you travel back in time, and you murder your grandfather before your mother was conceived. Well, if you managed to do that, then you would never be born, and so you would never travel back in time to make the attempt. And so it looks like you both do and do not travel back in time. You both do and do not kill your grandfather, and so on and so forth. And so some people think that kind of thing, if there are time machines, that kind of thing could happen because that kind of thing is impossible. Well, then there couldn't be time machines, right? It's sort of like a reductio ad absurdum argument for the existence of time travel. I don't think that that's right. I think that the universe can sort of maintain itself and keep itself consistent and stop sort of weird paradoxes from happening. But black holes make the point even more pressing because they potentially, take what's the sort of rumination in science fiction about whether or not you can travel back in time and kill your grandfather into something that's a little bit more down to earth and maybe like physically possible, depending on how black holes work.
Can you explain the mechanism that theoretically should allow this?
Yeah, so in general relativity, which is the theory of how space-time works, you've got a description of the spatiotemporal manifold, which is you could think of it very loosely as the kind of fabric of the universe. It's the thing that we move around in, the thing that we interact with each other through. We're interacting with each other through space-time right now. And one of the things that we discover in general relativity is that matter the shape of space and time. So if you've got a whole lot of matter in a region, it's going to actually bend space and time around it in such a way that your path through the universe will bend because the universe itself is kind of bent. And what this actually gives us is an account of gravity. So if you think of the Earth, turns out that the Earth has a big gravitational decent gravitational field. It's not the biggest there is. And what that does is it creates a gravity well around it. So you've got a dip in space-time around the Earth. And, if you imagine sort of like walking down a hill and falling down the hill, every time you get to the edge, you sort of keep falling to the center. Well, that's why we sort of stay stuck to the planet, right? Because it's sitting in this well and we kind of keep falling towards the center. And so like the universe has this really interesting feature where matter and energy bend space. Now, it's sort of easy to conceptualize with space, but it turns out that time also gets bent. And this is why if you're in a really strong gravitational field, time will get stretched in such a way that your clock will slow down compared to the clock of someone who's in a weaker gravitational field.
Right.
And sort of
and I always think of Interstellar, right? The movie Interstellar, where they were close to the supermassive black hole. One day for them was 30 years for people not near the black hole.
That's right. Yeah. So if you're close to this, one of these strong gravitational fields, you'll get these kind of time dilation effects. And so that's still all sort of, okay, we can sort of get our heads around that. We've got a bit of a feel for relativity. We've watched Interstellar. But, if you think about this notion of stretching and bending, well, if you think about an object that can stretch and bend, well, it can stretch and bend into you can take an object like a piece of paper and you can bend it right round so that it sort of connects. The two ends connect to form a loop. And in very rough terms, to give a deeper sense, we'd have to sort of dig into the mathematics of general relativity. In very rough terms, black holes are so big, so massive, that they bend space and time to this degree where they create these temporal loops.
Well, people ask me this question, like, if I could travel faster than the speed of light and I was trapped inside the event horizon of a black hole, could I escape? And the answer is no, because all of the pathways still lead you into the singularity. Like, whether or not you're going faster than the speed of light, space-time itself is tangled up and looped up to the point that you're not getting out.
Yeah, it's true if you're traveling at subluminal velocities, right? So a black hole will trap all light. So it'll mean that in order to get out of the black hole, you would have to travel faster than light. So it's necessary. Could you get out of a black hole with a faster than light spaceship? Maybe. It might depend on the black hole. It might depend on how much space and time are bent. But at this point, we're sort of asking questions that it's not clear we can answer with relativity, because relativity doesn't really give us a good sense of what's going to happen if you start traveling faster than light, because it sort of says that you can't do it. It says you can't accelerate up to the past the speed of light.
And so to have a loop of time, is this within the event horizon, or is it outside?
It would be within the event horizon, as far as I understand it. And so, the event horizon is the point of no return. That's the point at which space and time are so bent that light can't even escape. So if you think about this well, you think about there's a point at the edge of the well where you're just going to fall in and you're not going to be able to climb back out. That's sort of what the event horizon is for a black hole. And so the loop would be beyond the event horizon. So you could, so it's sort of like the time machine is there, but you can't really use it, although we don't really understand black holes. So who knows? Maybe there would be a way to actually get in and out.
Yeah. Practically speaking, you're going to get spaghettified. It's a high energy environment. Like, it's just a nightmare to get there. But I think it's interesting just from a time dilation perspective. Like, the closer you get to the black hole, the more, I guess, the less time you experience in that extreme environment, and you watch the universe speed up out there around you. And so you're definitely traveling forward in time as you get close to the black hole. Yeah,
you can definitely travel, and you don't even need to cross the event horizon to travel forward in time. Forward in time. This is sort of tricky, because I think there are two ways to think about traveling forward in time. One of them is like, if I want to travel into your future, right? So I can do that by getting in a spaceship, traveling away from the Earth at half the speed of light and coming back in a round trip. For me, maybe a few weeks would have passed. For you, 20 years would have passed. So I'll have traveled into your future in that way. And that you can do by just like going near a black hole, because the gravitational field is so strong, it creates the same time dilation effects, and you don't need to cross the event horizon for that to happen. If I want to get into my own future, that's different. And it's not clear that you can do that using the sort of same relativistic mechanics or using a black hole, because in that case, I've got to somehow get into my own forward light cone, as we would think of it in relativity. And it's not clear that we have actually a way to do that in using black holes or any kind of spaceships or anything like that. So it's a little bit different. There's something about your own timeline that is harder to travel into compared to the timelines of other things.
So how do you think about time in general? I mean, you mentioned that, you describe yourself a bit as a philosopher of time. What does that mean?
Yeah, what is it? How do I think about time? I guess I think of time as in our heads. If I had to, put it very, very quickly, I think that time is something that we are projecting onto the world rather than that something that's out there in the world. I think that when we've been talking about the way that some things might be kind of perspectival, might be to do with us rather than to do with reality. I think time is something that we're using to measure different kinds of interactions and effects and causation and goings on in the world, but it's ultimately something that that's coming from us rather than coming from the world. That's a fairly unpopular view. Most people, I think, are going to think that time itself is out there and it's not coming from us. But I guess I'm sort of driven there because I think time causes a whole bunch of problems when we're trying to think about general relativity and quantum mechanics. We're trying to bring them together, and maybe the best thing to do is to just kind of get rid of it. What then?
Well, hold on a second. So if you got rid of time, if time just didn't exist in math, how would that solve problems?
So if you look, I mean, there are going to be different answers to this depending on who you talk to. But if you look at quantum mechanics and general relativity, one thing that you can see, I think, is that there are different time variables operating mathematically in the two theories. So in quantum mechanics, you have arguably something that looks a lot more like a kind of Newtonian time. This idea that things are happening, in a sheet of time that covers the entire universe and marches forward. And the reason it looks a little bit like that is because when you measure a particle in an entangled pair, it seems that you get information about the other particle kind of instantaneously. And it looks like for that to be the case, you kind of need to make sense of something kind of like things happening together at exactly the same time in this kind of uniform way. And so it looks a little bit like quantum mechanics might have a kind of Newtonian conception of time, but of course relativity's got this relativistic conception of time, and those two things are just incompatible. And so if you've got these two theories that are operating with different notions of time, and part of the problem with reconciling quantum mechanics and general relativity has something to do with the fact that they've got these two different notions of time, well, it may be that a more fundamental theory just fixes that problem by getting rid of the thing that's producing the conflict in the first place, by just getting rid of time entirely and replacing it with something else. I mean, that's that's one way that you could see getting rid of time as something that's sort of useful for physics.
If, many people are searching for this, as you say, sort of a quantum gravity idea, what will it look like to say, okay, the problem is solved? Like we don't know what the answer is, but we could look at it and go, that seems correct.
Yeah, I mean, I think this is a difficult question because I think that there are lots of different things that people might be looking for in quantum gravity, and it's not obvious to me that it is a kind of unified program or as unified as some of the way that I've been talking makes it out to be. I think it's actually, there are lots of different things that people are trying to do, and so there might be sort of different goals that satisfy it. But I think the core thing that people want is to be able to, so we've got all of the forces, strong force, nuclear force, all of those things. We've got these like various fields. And we can give a quantum account of all of them except for gravity, right? The gravitational force just resists having a quantum story, which means that we sort of can't use the mathematics of quantum mechanics to describe how gravity works. And I think people would be satisfied that we've got a viable quantum theory of gravity if we managed to get a theory that gave us an account of how the gravitational field could be told in quantum terms. Now, in fact, there is a theory that does this, which is string theory. So string theory takes the various fields and particles that we have in quantum field theory, and it says these things can be understood in terms of strings vibrating in up to 11 dimensions. And one of those strings is the graviton, and the graviton is the thing that mediates the gravitational field. And so you have a particle that is responsible, or a string, responsible for gravity. And so, string theory has that. So it's necessary, I think, for getting a theory of quantum gravity that we give an account of the gravitational field in quantum terms, but it's not sufficient. What I guess ideally we would like as well is empirical confirmation of whichever theory we get. The problem there is that we have no empirical data to test, and it's not obvious that we will be able to develop empirical tests that can actually confirm or disconfirm theories of quantum gravity. Maybe we can, but we're talking about theories that, if they make predictions at energy scales that are, several orders of magnitude beyond what we can currently probe using the Large Hadron Collider. So we'd have to build something that is even more precise and high energy than the most high energy device we've ever created. Maybe we can do that. It's not obvious. And so I think empirical confirmation plus a quantum account of the gravitational field is what we want, but I don't know. It's not clear how we're going to actually get that second thing, the first thing, empirical confirmation, which means that we're in this situation where we're kind of trying to use a mixture of physics and philosophy, I think, to work out which theory to accept, right? Like how to make the best way forward. Another possibility is that we find some kind of very ingenious mathematical route to the problem. So it could be that we find a deep unifying piece of mathematics that draws our theories together, and we sort of get led to the truth via mathematics, and that wouldn't be the first time that's happened.
Well, particle physics is at this crossroad. The standard model of physics has been beautifully tested and demonstrated, and the Large Hadron Collider nicely put in that last puzzle piece, gave confirmation to Six Sigma that the particle as predicted is actually there and the standard model is complete. And yet this search, the hope that there would be a hint of maybe some kind of supersymmetry or some kind of other particle, some kind of dark matter, something that would begin to bridge the standard model, try and bring together quantum mechanics and gravity to extend the standard model, so far has failed. Like nothing, just silence beyond the standard model. And so now it's not just a philosophical question. People are looking to spend potentially tens of billions of dollars to build an upscaled version of the Large Hadron Collider and just start smashing randomly to see what you get. So what does philosophy say to suggest a way forward after reaching this seeming endpoint in particle physics as we understand it?
Yeah, I think I can give you a couple of different answers depending on your philosophical perspective. So I'm gonna zoom right out to a kind of like pragmatic come ethical response here, which might be maybe don't build that bigger machine. Is it worth it? Is the question, right?
Yeah.
I think that's a question we should be asking. Whether it's going to, we've got other pressing matters, right? We're facing very serious problems with climate change, and to spend billions of dollars building another atom smasher when that money could go into something like producing new technology for climate, for managing the climate. I don't know. I think that we should be thinking pretty seriously about that. But if I set aside those. Well,
but you could also build, I always say you could also produce less cigarettes, you could produce less aircraft carriers. It's not, only science experiments, money has to flow back and forth.
No, that's true. But we are talking about a pot of money for science when we're thinking about how to distribute funds. And that's the sort of issue there. But I totally agree. Build less aircraft carriers, do all of that as well. But that's probably not going to happen. What we do have control over in science and in academia is actually where the money goes for science. But coming back to the sort of more physicsy angle here, what do philosophers say? I think philosophy can help to sort of think about the epistemology of science. So like how it is that, again, the scientific method, how it is that we might come up with ways of testing or studying these theories or studying things like quantum gravity or quantum mechanics that don't involve producing maybe these big machines, and whether there's a way to do that. So there's some really interesting work being done on like analog simulation, where, for instance, with the black hole, it turns out that there's this thing like called a dumb hole, which you can produce, which is a kind of acoustic version of a black hole. So sort of a waterfall, which like seems to wipe out sound in kind of the way that that black holes wipe out light, and they seem to have a lot of the same properties. And so you can sort of study, some people think you can study black holes by studying these analog objects. Other people think you can't. And there's a kind of debate happening in philosophy at the moment about whether or not you can sort of get a grip on, the nature of black holes and how they work via using these other things. And what's interesting about that is that black holes themselves are probably something that is going to give us some insight and understanding to do with quantum gravity, because black holes are in the realm of both theories. Both quantum mechanics and general relativity have something to say about black holes. And so, for the most part, general relativity and quantum mechanics are kind of talking about different things. Quantum mechanics is talking about, particles and particle interactions. General relativity is talking about the large structure of space-time. But you get microscopic black holes and you get black holes in general relativity. And so they're sort of there in both theories. And so studying black holes might be another way forward rather than building, atom smashers. And so philosophy can help there with the kind of epistemology of these things. It's also, I think, scope for philosophy to help work out how you might empirically test certain theories of quantum gravity. So if philosophers can get their heads around these theories, then maybe they can help scientists come up with ways of actually empirically testing them, new ways of empirically testing them. So I think there's sort of work there for philosophy to do. But yeah, that said, it may just require building this giant machine and smashing it together and seeing what happens,
But when I think about like your background, and Sean Carroll is another example, right? Sean Carroll comes from a physics background and just can't stop thinking about philosophy, and so has made his own position at a university and is trying to bring that philosophical reason to it. It takes so much training to understand the physics to this level. The current state of physics, be it particle physics, relativity, etc. What's the best way to approach that? If these philosophical ideas are interesting to people and they want to work at that cutting edge of physics, what's the best approach? Get a physics degree first, then philosophy, or vice versa?
Yeah, I mean, I think you can. I mean, I either get a physics degree and then do philosophy, or do philosophy and then get a physics degree, or do philosophy and pick up physics. You don't need a degree in the thing in order to understand the thing. But studying both, I think, is important. But there's also something to be said for collaboration between people. If I know a lot less physics than a physicist because I'm not a physicist. A physicist knows a lot less philosophy than I do because they're not a philosopher. Together, we know as much as we need to about the two fields. And so, just getting people to work together, I think, is the shortest route to bringing philosophy and physics together. And that's sort of what I try to do. I try to make sure that I'm not just talking to philosophers, I'm talking to physicists as well, and that we're trying to build those bridges, but it's difficult. And part of the reason it's difficult has to do with the sociology of universities and the academy. There's a lot of reason to specialize, because that's how you get a job. You publish within your specialization, and publication is, the way that you get a position at a university. And there's not a lot of motivation to actually reach beyond your specialization, even within your own field, let alone between fields. And so the kind of sociology of universities really needs to change in order to facilitate the collaboration between people working in interdisciplinary areas. And universities, I just think, are classically bad at managing interdisciplinary collaboration. So I guess the shortest route is let's work together. That way you don't have to have individuals spend, if you do a PhD in physics and a PhD in philosophy, you could be spending 14 years studying. Yeah. Right.
But it really feels to me that as our knowledge becomes more esoteric and as the experiments become more complicated and expensive and we are removed from directly observing the results by several levels and layers at this point, that approaching it systematically, very carefully, philosophically becomes more and more important. It's almost like if you're looking for your keys, you don't need the scientific method. You don't need to check in and do double-blind studies and make sure that you don't have any key biases that are going on here. But when you are smashing particles together in a $40 billion experiment, you've got to be really rigorous or else that money is being lit on fire. And so it feels to me like having philosophers watching over the shoulder and pitching in at this point is more critical than it's ever been.
Yeah, I mean, I'm not sure I want to paint it as philosophers are there to ensure that things are rigorous. I think, physics
they're there
and math,
to help.
They're there to help. I think what they're there to do, what they can do is to help to sort out assumptions. I think, we've talked about biases, but there are also assumptions, and assumptions aren't biases necessarily. They can be, but assumptions can just be things that you accept uncritically because maybe that's how things were taught to you. Maybe that's how things have always been done. Maybe that's just sort of guiding assumption of the area that you're working in. But sometimes those
obviously whales are fish.
That's right. Obviously whales are fish. But sometimes that stuff just gets in the way of doing science. And the key moments for me where science has made huge advances have been where we've taken something that we thought was true and we've shown that it was false. And philosophers are very good at saying, well, look, have you thought about this being false? It sounds crazy that it might be, but maybe it is. Let's think about it.
Yeah.
And I think that that's the kind of perspective that can be really valuable in a scientific situation, is someone who's willing to just take anything and say, well, what if it's false? What if this isn't the case? What if there's another way that things could be? And there are very good reasons why scientists are just not in a position necessarily to do that, because they've got to work with something, right? Whereas philosophers, we can work with nothing and we can just sort of happily go along thinking about things. And I think that that's a kind of creative space that can be quite valuable. Of course, we might end up doing a lot of stuff that is just bananas, but maybe along the way we'll do something that's useful too.
Yeah. I mean, back to that idea, just like the more esoteric the knowledge is, the more you have to be able to recognize an assumption that someone is making, because a person will be putting in some number, some formula or whatever, or assuming something in their experiment. You're like, whoa, neutron decay? What if that's not really there, right? But a philosopher who isn't necessarily trained, hasn't gained that level of knowledge, won't be able to catch the assumption, because it won't even recognize it as a piece of knowledge that is being assumed.
That's right. Yeah, and I think a lot of that is, we talked about training in physics, but training in mathematics I think is super, super important here, because if you don't, a lot of what happens in physics is people staring at the math and reading things about the world off from the math, and it works surprisingly well. But sometimes it doesn't work, and you've got to have a sense of what's going on mathematically, I think, in order to really understand a lot of what's going on with these physical theories. And philosophers actually do have quite a strong association with mathematics and tend to have, in some cases, quite good mathematical understanding. And so that helps as well. But of course, not everyone does. And I think that's sort of part of the training. But again, you can collaborate here. You can bring in mathematicians as long as you have a common language that you can talk. And that's often the hard part, is finding common ground. Once you find that common ground, I think it can be very fruitful to bring people from, different areas together to talk about something like a well understood physical theory.
Mm-hmm, mm-hmm. Yeah, I think for a lot of scientists, and you probably get this, there's a certain amount of eye rolling with this idea of philosophy at all.
Yeah.
Right.
Yeah. I've seen it.
You've seen it. Yeah, of course you have. And yet, the scientific method is a philosophy. That there's only one way of knowing the universe, and there are several, but it's the one that gets results. And and it's not done, and the work isn't done. The scientific method is unfinished. And like I think all sciences, it is being refined to sharper and sharper point as a better and better tool to deal with the state of knowledge and our state of scientific inquiry that we're at. And it has to go hand in hand, that it can't not continue along the journey that it started 500 years ago.
Yeah, and I mean, I think
forever.
I think what I like to remind scientists of here is that, 300 years ago, science was called natural philosophy. And it was called natural philosophy because it was done by philosophers who were doing science as well. I mean, the sort of split between science and philosophy is really a 20th century invention, I think. Even Einstein, you look at Einstein's influences. Einstein was heavily influenced by the Scottish philosopher David Hume, who's, David Hume's whole thing was the world is just relations between stuff, like very roughly speaking. And, Einstein's theory of relativity really takes that very seriously. And Einstein is in places explicit that his thinking is influenced by philosophers. And so, science has always been developed in collaboration with philosophy. And, as science has become increasingly more specialized, what you've seen is people who can make progress in science without thinking about philosophy. And, that's perfectly fine. But at a certain point, when we get to these areas where, the very thing that we might need to update is the scientific method, then I think it's time to turn back to sort of more philosophical matters and to, have another look at the foundations of science, which is what, we're here to do and here to help with. But yeah, there's a lot of...
Yeah, I mean,
there's a lot of eye rolling, but it's sort of par for the course.
Yeah. No, but I feel like it's analogous to like driving a car that you don't understand, and it works great until the car breaks down, and then you don't know what to do now. Right.
Yeah. I mean, I want to give science a little bit more credit than that. I mean, I think scientists are very good at fixing their own car as well. But I think philosophers can. I think they just have something to say. Let me put it that way. That we have tools that we can use that can help look at these things in a different way and maybe expedite the process a little bit and speed up some of this critical reflection.
Well, maybe I'm a bigger fan of philosophy than you are then.
Maybe. That would be ironic if true.
Yeah. I honestly do. I really think that the two work hand in hand, and that process of philosophy of thinking, as you say, thinking about our assumptions, thinking about our biases, thinking about our techniques, thinking about how we replicate all of those pieces, thinking about how we think about what is at the next level, what are the implications, all of those, that job gets harder and harder and harder as the science gets more and more abstract. And yet we see the results of a universe, or we see the results of our modern society is based on very abstract scientific discoveries. Here we are talking on computers that use fiber optic cables to communicate across continents, computers that are with, wire sizes measured in the nanometers, where electrons are randomly jumping from one wire to the other. Like it's tough work to get to this point, and to make progress also requires rigorous thinking. And in many cases, I think the rigorous thinking gets more rigorous the more abstract and the more complicated it becomes. So
yeah, look, I mean, I agree. I think philosophy and science do go hand in hand. I think that the sort of thing that you're pointing to, the sort of abstract nature of science, I think part of that, one way of thinking about that is also the kind of more detached it becomes from direct empirical observation. And you pointed to that a little bit, like the more we're sort of like several layers of inference deep when we're thinking about, you take the Large Hadron Collider. What does that actually give you? It doesn't give you what people think, which is like a nice diagram or video of things smashing into each other. And then like you go, oh, look at all the bosons that are flying out. It doesn't give you that. What it gives you is data, raw data that you then have to interpret and build into models. And then you kind of infer from that data after you've run like background statistical tests to make sure it's not complete junk, that there's something going on. And like, because those several levels of deeper with respect to inference at that point, each step in that chain of inference could be faulty and needs to be considered. And that's where philosophy can help, because one thing we're good at is
100%.
looking at how inferences are made and whether they're good or not.
All right. Well, then maybe we agree. Maybe we are equal fans of philosophy.
I hope so.
Well, Sam, what is your next project that you're working on right now that people would want to check out?
So the thing that I'm working on at the moment is the idea that causation, which I think is a really important notion, is actually the most fundamental thing in reality. So I've talked a little bit about how space and time might not be fundamental, might be the sort of most basic thing that there is, but I haven't said much about what might be basic or what might be fundamental. And causation, which I think of as this, when you change something, something else changes, very roughly. That's what I think of as causation. I think that is an extremely important principle. I think it's extremely important in physics. I think it's extremely important in philosophy as well. And I think that you can demonstrate how space and time come out of thinking about the world at the most fundamental level in causal terms. And so a lot of the work that I'm doing at the moment is looking at the relationship between causation and space-time, and working out whether and how simply by understanding causation a bit better, we might be able to make progress in thinking about the nature of space and time. And so I'm working on a book on it at the moment, doing some collaborative work with some folks in Switzerland, in Geneva. We're doing some sort of running some conferences and workshops and things like that. And that's the sort of direction of things at the moment.
That's really cool. I mean, it's such a tricky idea. I mean, obviously that starts to shift into that religious conversation that people have about causes all the way back to the beginning. How do you get a first cause? But like how, I mean, can you give me sort of an idea of how this would manifest in terms of like causation, giving these kind of practical outputs in the universe?
Yeah. Okay. So let me think about maybe the best way to do this.
Something that you're putting in your book.
Yeah.
There must be some analogies in the book that you're using.
Yeah. Well, okay. So there's actually maybe one of the better ways of thinking about it. There's some really interesting stuff that was done by Stephen Hawking and a couple of other physicists in from around the 50s to the 80s. Where they looked at general relativity, and in general relativity, it seems like you have causal structure embedded into space-time. So, for instance, if I want to get to Rome, I can do that so long as I take a certain path, right? So there's a sort of like causal process that will, if I initiate now, will get me to Rome. But it will take time to do it, and I can't get there instantaneously. And relativity sort of puts constraints on the way that causation works, like the way that you can sort of which things you can causally influence and which things you can't causally influence. And roughly things that are too far away from me to like reach with any signal traveling below the speed of light is something that's causally inaccessible to me, but all the things that I can reach at signals traveling at or below the speed of light are kind of causally accessible to me. So general relativity seems to have this like causal structure baked in. And so what people like Hawking showed is that if you start from causal ordering, so you think about your life and you think about the fact that you're born, and then you were 3 years old, and then you're 5 years old, and there's a sort of causal ordering, and you can like write down a timeline of your life with all of the causal steps. Well, what Hawking and these others showed is that if you have some structure like that, and you put that down first, and you kind of think of the universe like that, you can think of it as this sort of like causal system that unfolds. If you have that structure, then you actually get back a lot of what you have in general relativity, all of the other stuff, like the metric structure, the spatiotemporal structure, all of that stuff can come out up to a certain point just from this underlying causal structure. And that's a kind of interesting fact about general relativity. In the early 90s, there was some folks who were working on quantum gravity, who like one of the strategies you can take to developing a theory of quantum gravity is to take gravity and sort of, start from a bunch of discrete building blocks and try to rebuild the universe from like little chunks rather than like a smooth continuous object, which is how we usually think of space-time. And so there's this theory, causal set theory, and what they do is they use these sort of, like, riffing on these results from Hawking and others, they try to show how you can rebuild space-time using just causal orderings, just discrete structures of causal relations between things. I find that very interesting because what it suggests is that this causal picture, this sort of like timeline that you might write down, that might be the most basic thing, and then out of that you can sort of recover space and time. So that's
so you could kind of connect everything in the universe in this almost like a pyramid of where each stone is sort of resting on the other stones below it.
Yeah, sort of like a causal pyramid, if you like, leading back to the Big Bang, and then everything is sort of like causally dependent on it. And like, but we sort of think that the way we usually think about things is that you sort of lay space and time down first, and then causal stuff propagates through space and time, right? It's a sort of like medium through which causation happens. On the sort of picture I'm interested in and the picture I'm trying to develop, you start with causal structure, right? You lay down, you start with things that are interacting, and then things that are interacting, out of that emerges space and time, which is sort of like you're reversing the usual way that we think about causation, space and time. Rather than thinking of causation as thinking of space and time as basic and causation coming out of it, you think of causation as basic and space and time coming out of them. So that's the sort of, that's not exactly the thing you asked for, which is like an analogy to sort of get us in the mood.
Yeah.
But I guess it's hard to give an analogy because we're thinking about things that are really, like, we're thinking about a kind of reversing two fundamental concepts in the way that we usually think about them. I can give you analogies for how causation works, but not quite for the way that I'm thinking of causation in this context.
Well, we'll have to read the book then.
Yeah, maybe.
Yeah. Well, Sam, it's been an absolute pleasure talking to you today. If people want to sort of follow your work, see more of your thinking, what's the best place to do that?
The best place to do that is probably my website, which you can just find by Googling Sam Barron Philosophy. There are a couple of other Sam Barrons out there. There's some that are much more famous than me. So
yeah, as an actor,
there's an actor and a director. So you have to like sort through till you find the more mundane one. So that, but also I publish stuff pretty regularly on The Conversation. And so you can sort of follow me that way, or the Australian Catholic University's website also provides a fair bit of information about me and my work. And I'm also on radio, so I don't know. You'll probably just run into me. I think is probably the way. Just live your life, and you'll come into contact with me somewhere.
Live your life, and now you're aware of Sam, and he will just show up when he's most needed.
That's right.
To help you work through a tricky philosophical problem.
That's right.
Awesome. Well, Sam, thank you so much for taking the time to chat with me today, and good luck sorting out the entire universe.
Thanks, Fraser.
Okay. Bye-bye.
Bye.
You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.